Okay, thank you. So it really is a pleasure to be here, and I'll apologize in advance. This is the first talk I've given since the pandemic outside of sunny Cambridge. So I apologize. So I'm sort of I feel like a graduate student almost, and sometimes in front of an audience of people that, and I know many of you, and many of you know me, so you will make allowances for me. And if I speak fast when I'm nervous, and I was speaking to my mother, feels very guilty that she didn't send me on some sort of training as a child, and she still tells me that. Okay, so I'm doing this on behalf of really a large number of people. The group at the top are people who've been actively working on the VHS data in the last 5 or 6 years, but really without, VHS would not have been possible without the VISTA telescope team. Will Sutherland was a project scientist. The camera team, actually I forgot to put Gavin Dalton's name on this. Mike Irwin's group in Cambridge, and the Wide Field Astronomy group. Nick is here today. Nigel Hambley was probably one of the founding members, and obviously, impossible without the various ESO teams involved at all levels of this project, and you'll sort of realize when I come to the next slides. And then really a special thank you for Jim Emerson, who was the VISTA project PI, and Andy Lawrence, who was the chair of the VISTA Science Committee. So it's sort of interesting. I went back into my Dropbox folders. This is a slide from a talk I gave to the STC here at ESO before the UK acceded, I think that's the right verb, to ESO. Basically, we had obtained funding from the VISTA telescope from the UK government in 1998. And at that point, we were looking around, we wanted a site. We'd chosen the Southern Hemisphere, and we basically visited ESO to basically show our wares and this, I still have this PowerPoint presentation. So I'm going to use some of those slides today to start. My first sort of document, I don't know if Tom's here yet, actually. This was the VISTA Science Committee document 01, which was a site choice. So we basically did a report without visiting. There was no donkeys or anything. That's like the classic photograph of from ESO, and I saw its 60 years anniversary of ESO in Chile. So we were looking at Paranal and Pachon, and basically both sites they came out more or less equal. Paranal is slightly warmer, but but the seeing was better. So, and the K was a concern. That was the temperature was a concern at K, and so basically that's one of the reasons why UCURT has the K filter, and VISTA uses the K short. And these were very, some of you will know what I'm talking about, but it's just the thermal background is really one of the limiting factors in the K band. VISTA was probably the first agile project that I was involved with. And basically, this was our Gantt chart that went into our proposal back in 1998. And we were going to complete it all in 5 years. Of course, that is your classic agile project where you've got X pounds of money. The money says you have to spend it in a certain period of time. So you write a proposal, with those constraints, of course. But a plan is important. The key change, which followed on from the ESO workshop meeting, was the original camera had an infrared imager and an optical imager. And that had actually the output of that. So I just go back to that. So the consequence of us, in some sense, getting permission from ESO to put our telescope on their site before we joined was that ESO had the VST, so there was not seen as a strategic need for ESO to have yet another wide field imager. And so what we did was, we were told, I think, or negotiated, the infrared imager initially had 3x3 detectors, so we went to 4x4, and we dropped the optical imager. And that has two consequences. We now had more infrared chips, and you had more nights. So the surveys that we were planning could effectively go 3 times faster, or we could do 3 times as more infrared science. There was a tweak done to the pixel size, so it wasn't totally one for one. And this is one of my favorite pictures of Vista. This is a picture of the telescope mirror being delivered down into the dome. And thank goodness there were no earth tremors. So already you can sort of see the project had slipped from the original plan. Again, these are slides from way back when. I won't talk about how old I was then, or even some of the audience would be worried about how young they were. But I certainly won't discuss my age back then. Basically, we wanted a world-leading, the specification was really looking forward. At that point, of course, we wanted a camera to be better than the VST because we hadn't decided at that time that we were going to actually come to ESO, basically, and we wanted to maximize the speed in terms of survey power, but also to actually maximize the possibility for basically breakthrough science. This is just a comparison of the other facilities at that time, and it really hasn't changed fundamentally. These were the other wide field imagers that existed at that time or were in the planning phase, because I think NIRMOS did not happen with the VLT. But it was interesting, the comparison, and these were sort of prototype. This is a camera we built in Cambridge, which was the first infrared mosaic. So we were developing the technology, so it represented a factor of 10 uplift, and it was comparable basically with the VLT, except you get all the nights on the telescope, and that's always an issue when you build an instrument. How many nights of time can you get to that instrument? And ESO grapples with that very effectively by having sort of 4 telescopes effectively and 3 foci. And so then this was the sort of equivalent to field of view time. This is my metric. Or it's a standard metric, which is just the grasp, which was the area times the telescope, times the field of view. And so this 5.5 is the metric, what you get whenever we upgraded actually to 4x4. But even then, back then, we were thinking of actually upgrading to 5x5, possibly, if someone came along with the cash. There were also issues actually even getting the detectors in those days. This is just the program. Okay, then this is just another comparison, just to give you an idea of what a leap the 4x4 was on other facilities. You have Isaac, the VLT, Nick Moss, this is the moon. Someone else has shown this slide. So this is WIFCAM, and then this is the Vista one footprint. Now, one of the design changes that we had to do was all the previous mosaics had, you basically put the spacing of the detector. You cannot butt the infrared detectors and those generation of infrared detectors. So therefore, you just deliberately put a spacing of 90% or so in, so that makes the mosaicing easier. In order to squeeze 16, even though we said 5x5 in the concept study, to get 16 in and have your autoguiders, quite often people forget. When I was younger, my colleagues couldn't understand why you have to have an autoguider, but actually we wanted to get sub-arc second seeing, so the autoguiders and the wavefront sensors sit down here and here. So this is a circular field of view, but we couldn't put the detector. So what we had to do to maximize the area of detectors was, this is about 90% and this is 45%. And this was driven by the sort of design, and that has consequences for the data reduction and features in some of the surveys. So this is the camera. Before it was, but actually this is probably not the camera. It's probably, obviously it's not in the Dewar, so it's probably not got the detectors. 0.34 arc second per pixels. It's a sparse field array. This is just again the same thing. And then this is what you get when you take. So we call a single image is called a paw print. And so basically I've written this down. So you take 6 pointings to give you a contiguous tile. That each pointing gives you 0.6 of a square degree, and the final tile, and red actually here is high exposure. And this is an exposure time of 1. So these are all doubly exposed by 2 pointings. And so, that's sort of, it's complicated, but it's the pipeline processing obviously has to, well, the astronomers have to deal with it. Okay. So here's just now I'm going to go into the VHS survey goals. You know, the high-level goal was to survey the whole southern hemisphere in at least 2 near-infrared bands when combined with the other wide area surveys. So VVV, VMC, and Viking. Modulo, I mean, I'd assumed really that somebody would fill the gaps in. We defined the galactic, our limit as being galactic latitude 5 degrees. So I'm glad that that gap has been filled in. Okay. Then we were optimizing for other optical surveys because the V and Vista, of course, is visible. So we were always thinking we want to get the visible as well. Extragalactic astronomers need visible. It's probably less important for towards the galactic bulge, which is highly obscured. And so there's basically 5,000 square degrees of the dark energy survey, which actually, as a member of the dark energy survey at that time, we put a separate proposal in. So I was on competing proposals, which were then merged by the PSP review, and we excluded the Viking footprint. And so, you know, we wanted to be deep. The first really deep survey, it's 5 magnitudes deeper than 2MASS, and fundamentally it's a legacy survey because Euclid will come along and go deeper, but now ESO has the first epoch in the infrared. Just to give you an idea of comparison, not many people appreciate the Sloan Digital Sky Survey. It's a 2.5-meter telescope. The exposure time is 60 seconds. Okay, you see how deep you can get in imaging. Your exposures don't have to be hours and hours to get down to the sky, just to get to reach sky, because the QE is higher these days. Be 1 hour on a photographic plate, which you started out on. So this is now there are 3 components to VHS. I'm just doing it alphabetically. I've mentioned the DES area. The other half of the high galactic sky, just ballpark numbers, I tend to think of the sky as 40,000 square degrees, 20,000 square degrees in the north, south. Above galactic latitude, there's 20,000 square degrees. So I always tend to work in those sort of fractions of 10,000 square degrees when I'm designing strategy. So the DES footprint is 5,000 when you include the Viking. Then there's the other part, what we call Atlas, which is just the other part of the extragalactic sky, and it now has VST Atlas data. Again, the survey was agile in the sense that we started out with exposure times from the ETC. After the first year, we discovered that we weren't getting the depth in J that we expected, and I can't remember whether that was sky brightness estimates or not. So we dropped H, basically, from those surveys that were doing it, and put that time into J, and that went through. Okay, so that's when I come to the coverage maps, you have to bear that in mind. So there is H, but only for the first 2 or 3 years. Basically, the H sky, those of you who work in it, it's very variable, and in terms of AB magnitudes, it can be brighter than K. K is determined by your thermal background, but the air glow determines your H, and it varies during the night. It tends to H-band skies, get the old air glow gets pumped up by the atmosphere, so the sun. And then what we call the galactic plane survey. Some people will say it's not the galactic plane survey. But for extragalactic astronomers, and I apologize to the galactic astronomers for using that term, but we were basically above galactic latitude 30 degrees, and we excluded VVV and the VMC surveys. And this is just a table, this is data release 5, which is the current public release, to show where we were at before the pandemic. And then what I've gotten here is also the Z and Y from the dark energy survey. The blue ones are coming from the dark energy survey, and because we always plan this in terms of the optical as well. And then this is the final release. Okay, so this is now just the Casio overview plot, which is in 8 of not in galactic coordinates, as mentioned before. So we have here the VVV survey, we have all the surveys. I guess VVVX coming along here, VMC here, and various other surveys. And so this is up to date to, so this now tells you the full, we've been observing with Vista post-commit. This includes, I think, the commissioning phase back in October 2009, right up to the last. So VHS I don't think had any data after the end of April, that period. I'm not too sure who was getting data, if anybody actually, because of this, and of course we had the gap for the pandemic. And just to give you an idea of the two, this is an overview really of the surveys, so maybe others. So this is the K-band versus, sorry, okay, I just got the K in that case. Okay, so this is now the VHS final coverage plot through our software. And so the different colors of green are just representing the different, effectively sort of depth or bands. So light green is the GPS, and this is the DES footprint. This hole is Viking here and here, and this is the Magellanic Clouds here. And these are, I think these are single tiles, which I'm still trying to find out why they weren't observed, or they're not in my files. And I've just had a chat with Michael. I believe ESO has filled these gaps in, and we've got to try and find those holes. Although that just might be shallow, to be honest. Okay, but Maria Rosa was quite upset that I hadn't filled the gap, and so we tried to track it down. But okay, and so then, this is what happened when I tried to make a few more plots last week. So I apologize. I got some sort of AstroPi ecliptic coordinate error, which I'm still trying to fix. So therefore, I'm just going to show you the DR5 coverage plots, which are, so I'll hopefully be able to update these slides later in the week when I went to Python 3.8 during the pandemic, and so not all my code runs. And so basically, and also AstroPi as well. So this is so just to give you, this is the all band coverage. So these are the gaps before that we've been filling in over the last few years. Okay, so this is the Y band coverage. So we covered Y, we didn't cover Y in the dark energy survey area because the dark energy survey has Y. Okay, so there's Y in this, but it comes from the dark energy survey. And we didn't do Y band observations in what we call the galactic plane. So Y was a high priority for the extragalactic sky. And so this is the J coverage. And as I said, it's been filled in since then. This is the H coverage, which, as I said, is partial. We started doing it, but then stopped it basically because basically it wasn't going as deep as we wanted, and we weren't going as deep as we wanted in J either. So that was dropped. I can forget the dates are probably on the plot. And this is their. As I said, I will try and update these. This is the K coverage, but most of the regions are all filled in now. And then this is just the our depths. You don't take we run Mangle on these and produce the depth maps and the seeing distributions. But again, we have to get that updated, and I hopefully will progress that here this week. So this is just the sort of range of the science from Milky Way science on low mass stars. VHS was used for targeting for the ESO Gaia survey because it was the only, well, not the only, it was sort of, at that time, it was the most appropriate survey to use. Okay, yeah, okay. And then Canveer et al. Most of the VHS science requires spectroscopic follow-up, and foremost, again, is coming soon and it's been used for its foremost targets. I'll just skip through the quasar stuff. Actually, this is quite a nice example of something we hadn't thought of. We've been doing a lens quasar search with Gaia data, and okay, there's a lot of stuff here, but the key thing is when you're looking for lensed quasars, when you don't actually know the object is even a quasar, you're just looking for objects that have multiple stellar sources and quasar-like colors. And so we've been using Gaia to do that. But unfortunately, there's a lot of foreground Milky Way stars, and they just project sometimes and can look like doubles and quads even in terms of just the randomness. Because lens quasars are 1% of all quasars. Quasars themselves are only less than 1% of the objects in any patch of sky. So you're looking for a very rare population of objects. And so this is just a set of multicolor renders from, these are 3 colors. This is GRI up to YJK. And the key thing is that we do image subtraction and modeling, and this is the lensing galaxy that is sort of visible in, well, certainly not visible in the G band, but it really is very clearly detected in the near infrared. And so what we do with our lens quasar search, if we find a group of stellar objects and we don't see a lens, okay, so we don't see a galaxy, we say that's not a high probability candidate. We actually are looking for the lens and the quasars, okay? And so that's been a very, very successful. Basically, we've, I think, well, doubled the number of lens quasars in 2 years, first 2 years of Gaia. And they've been used for sure, H0 studies, okay? Okay, so just that's more or less, I think, Vista Hemisphere. But since we're here, I think really thinking about the future, and I just wanted to point out a few other surveys that are relevant, and then I'll just mention LSST at the end. So this is the other survey that we've been involved in the UK, and Cashew Process and Edinburgh Wi-Fi Distribute there's a sort of the northern equivalent of VHS. So this is the coverage map for the WIFCAM surveys. This is all any band, and this is the J. And so there's a UKERT hemisphere survey. So the UHS was J, and then the K was then added, and that's shown here. So that's, I think, as of, I think it was released a few months ago. So we're now in a sort of unique time where we have really deep infrared surveys to comparable depths in at least J and H over the 2 hemispheres. And so it's discovery space. And then I just want to just highlight the optical sort of sky. This is using the legacy survey sky viewer. So it's showing the sky multiple times here. But the key thing is that they've been doing imaging in the north. This is, I think, 30 degrees north. So this is the DES footprint down here. And then this is, I think it's the BOC. DESI is a spectroscopic instrument, but they've been doing a survey using the dark energy survey camera as well. So this is their data release 9 in their sky view, which was, I think, from 18 months ago. And what they've done is they've actually taken all the DE-CAM data and put it through their pipeline. And so we now have, this is, I think, minus 90. And this is probably the clouds here. They probably haven't, because, well, I don't know why they haven't. I suspect that's just processing problems with the clouds. So we're now again in a unique position, really, in time, where we have deep optical surveys as well. Of course, the real problem is they're all in different archive centers, which is something I want to maybe talk to people in the week about. Okay, so the next steps for us, apart from delivering the data, the final release to ESO, is we're preparing, some of us, for LSST. So I'm just going to present some work that Raphael Shirley, who is now at MPE, has been doing. This is part of the UK's LSST funding stream. And this particular work, Amanda Banerjee, now at the University of Southampton, and Elam Sarami will be possibly mentioning some of this later in the week. Okay, but this is just, so what the basic idea is that at the limit of the VISTA surveys, we go to 5 sigma typically with the catalogs, but there's important information below 5 sigma in the 2 sigma sources. And so this is just showing, so this is a piece of work we did, so I'll remove the citations up here, that Amanda Banerjee did, where we tried to combine the VISTA and DES data. The problem is really, it's quite difficult because you've got different pipelines, different data products, It's a nightmare, and you discover you can't, it's not scalable, but thankfully LSST is going to come along. So this is basically just showing you that, the DES R band had 260 sources in this patch. The 5 sigma catalog in VHS-J had only 84, but we can get down to signal to noise of 1, which is sometimes just an upper limit, okay? Oh, sorry, I don't want to use that word, not upper limit, it's a flux, okay? You're not going to be working in magnitudes, hopefully, in the future. You'll be working in fluxes, so that you do a proper and Bayesian analysis on this. So this was some tests we did to justify development of a pipeline. And so what we're doing is we are working, Raphael is doing the work, and this is in collaboration with the LSST. We've got 2 pipelines here. This is complicated, right? It's not, but the idea is to have a software system where we're running the LSST pipeline is going to run on the cashew products, not process the data from raw, but basically you'll get images and at the right pixel scale, and the catalogs will be basically LSST products. They will just look like LSST products. That's the vision. So that we can, and so at the moment we're doing is we're using the Subaru data, which is somewhere up here, in the pink, so red, as a proxy. So we've been working with LSST group, but the idea eventually is that when we get the LSST data coming out of the pipeline, there'll be new Vista products delivered from that. And just to give you an idea of how complicated it is, and this is what's coming next, so these are, if you like, the Subaru pointings, which are circular. Underneath is the LSST data model. And the LSST data model has, every survey comes up with its own grammar and words. We have tiles and paw prints. So LSST have the concept of a tract. A tract is basically a square region, and inside that there are patches, okay? And each patch, so they just pixelate the sky, okay, onto a sort of grid. And so the idea is to do the same for the Vista products, basically. And Raphael has been working on that. Basically, the idea there is to have, you detect in any band, and then you measure in every band. So you'll get measurement and force photometry catalogs, deblended fluxes, and a whole range of, this is all coming out of the LSST pipeline. We're not developing this part, basically, so the idea is to align with the LSST. Okay, so I'm just going to stop at that point, actually. I have other slides, but it's good. Okay, thanks for listening. I'm really looking forward to the rest of the week.